So you need a quote on rocket and prime and
Good morning, everyone. This is Julie McDonald with Microcom Technologies. I would like to thank all of you for attending today's webinar with RF Elements. Today's host is Tassos Alexou. He'll be presenting today, and if anyone has any questions, please feel free to submit them in the question box, and Tassos will answer them at the end of today's presentation. Tassos, I'm finished for now. Please go ahead and take it over. The floor is now yours.
Thank you. Good morning. My name is Tassos. I'm with RF Elements, and today we'll be talking about increasing throughput. This is our Increasing Throughput 101 webinar. RF Elements is a company based in Slovakia in Europe, and we are the original creators of symmetrical horn antennas in this market, and we'll talk about our technology and how it will help you grow smart, reject noise, and save spectrum. So one of the challenges that we're facing today as wireless outdoor networks get more and more complex is really dealing with the demand for throughput. Over the years, the demand for faster and faster connections has grown almost exponentially. On top of that, it's not just the growth or the requirement for much faster connections, but it's also the number of subscribers is growing at an equally fast rate. So we're posed with the two issues: how to deliver more connections, right, and how to deliver higher throughput to those connections. And the following challenge to that is really the lack of spectrum that we have, right? So, you know, to cover the growing demand that's in the market today, new standards are being introduced with, you know, higher theoretical speeds, more complex modulation rates, and other techniques like GPS synchronization. But they all require more spectrum regardless. And spectrum is limited. And one of those reasons for the limitation is really RF interference, right? So you may have channels available, but are they really usable? That's the question. And, you know, again, wireless vendors are, you know, bringing more advanced technologies with, you know, complicated schemes like, you know, TDMA, active filtering to try and address these issues. But really the results are not sufficient. You know, even though new radios that have, you know, come to market with faster speeds still aren't addressing the number of clients per AP. So it requires much denser AP co-location. And we know that space is limited on towers and traditional sectors are fairly large. And symmetrical horn antennas are the answer for that, because you are able to co-locate, you know, more densely co-locate your APs on a tower in the same space of a traditional sector. So, you know, with the problem being RF noise, you know, again, you know, the vendors out there are not really solving this problem at the roots, you know, of the cause. They're kind of dealing with the consequences, which is really the wrong approach. A cleaner spectrum and more efficient use of spectrum is a much better approach rather than just gobbling up, you know, more spectrum with wider channels and stuff like that. So here are some examples of, you know, poor solutions that, you know, try to deal with the interference issues that we have. And currently, one of those, you know, methods is really shielding, right? Shield kits, these aftermarket metal cases that you put around your antennas to try and deal with noise and reject noise to some extent. One of the major problems with that is it's not the best approach, because actually what happens is it may create the, you know, the assumption of clearer spectrum or better spectrum at the AP, but these shields tend to really warp the RF signal out of these traditional sectors, which creates more noise, because now you're sending signal in areas that you really don't intend to send them to. So it's really kind of hiding the problem. It's than actually addressing the problem of interference. If we look at the radios of yesterday and the radios of today, we can see, what the mainstream vendor solutions are. The radios are growing, at a higher complexity with, again, new feature sets like GPS synchronization, active filtering, TDMA, wider channels, and really, again, the use of wider channels is just, again, consuming more spectrum, and it would be better served to be able to deliver a higher quality connection with less spectrum than gobble up more spectrum. So this is, we feel is the wrong approach for dealing with this issue. So RF Elements' solution, in dealing with the source of the problem is, again, rejecting noise and also reducing loss, almost down to zero loss. Our symmetrical horn antennas all have our proprietary twist port connector system, right? This twist port connector system allows you to eliminate the external pigtail connections between the radio and the antenna itself. Because the interface is enclosed, the interface is tuned, the interface is fixed, you really reduce signal loss due to poor quality cables, right angle connectors, and what have you. So twist port ecosystem, again, allows you to reduce your loss and then tap into our symmetrical horn antennas, which give you very clean antenna patterns. So we talk about noise rejection. Noise rejection refers to the ability of the antenna to, again, reject noise by not looking at so much spectrum, kind of making it immune. If we look at this simulation here, you can see on the left is kind of the 2D plot of what a traditional sector looks like. It's typically extremely wide, 90, 120 degrees, 65 degrees, and so on, and very flat. But these traditional sectors have very large and complex side lobes, and that's what's gives the antenna the ability to receive more noise than it should. Wider angle looks at more spectrum. Unintended directionality of antenna out the back and the sides also allow it to receive noise. If we look at the antenna pattern for a symmetrical horn antenna, it's clear to see that noise rejection exists because we have zero side lobes. So the antenna is only looking and only transmitting in the subscribed 30, 40, 50, 60 degree, whatever the width of the antenna is. It's only looking at that particular area. So it's not receiving noise from, again, unintended directions where the sector should not be listening, and also not transmitting in those directions as well. If we look here, this is a diagram of a parabolic dish antenna. It is usually used for point-to-points. And as you can see, parabolic dish antennas actually have extremely complex side lobes as well. So it's not just that main, 4, 5, 6, or 8 degree main beam that most people cue in on spec sheets, but there's very complex side lobes that pick up noise from co-located parabolic dish antennas, as well as much wider angles than the, again, prescribed main beam width that most people think. The other part is because parabolic dish antennas have such high gain, the side lobes for these parabolic dish antennas actually grow much larger in intensity as well. So their ability to hear noise at greater distances is greatly influenced by that much higher gain that the antennas have by default. Oops, sorry, I'm trying to advance a slide here. There we go. If we look at a point-to-point antenna that's built on horn technology, again, you can see those side lobes are 100% eliminated, and therefore, again, the horn antenna only sees and listens and talks in the actual, beam path that is spec'd out. So you get much cleaner connections, much higher co-location capabilities, so you're able to have many more backhaul links co-located on a tower with one another when you use horn technology versus parabolic dish technology. We talked about zero loss. Here you see a traditional setup. You have a radio with a pigtail interface that attaches to the antenna, and there's a lot of loss that's included in that setup. And not just the length of the pigtail itself, but the quality of the connectors, if there's loops in it, and what have you. So our zero loss system allows you to, again, eliminate a lot of those loss paths for the radio signal to hit the antenna, and therefore creates a much better system, a more efficient system. So if we look at traditional sectors, this is a patch array, traditional sector versus a horn antenna layout. So if we look at the way the beams actually work, you have two polarities mostly in MIMO. So you have a horizontal pattern. You also have a vertical pattern. And you can see that these patterns in traditional sectors are usually not identical. So you have coverage mismatches. Most of you have probably seen, as you have customers out at a greater distance or near the edge of the sector, you start getting spotty performance. And these low performance areas of the sector really affect the overall efficiency of your AP, right? So if we break up the coverage area, you can see that the center of the traditional sector has, the best signal. It's the most uniform. And as you go to the edge, you get, mediocre, then eventually poor signal performance, as well as when you're on the side lobes. With a horn antenna, the horizontal and vertical beam patterns are identical. So no matter where your customer, your subscriber is within that coverage area, they're getting a high quality connection. So this does a lot, not only to maintain consistent modulation rates across your subscriber base in that particular coverage area, but it also, ensures that with the frequency response of horns, that as you change channels, that coverage pattern is not changing as they do in traditional sectors versus horns. So now we're going to talk about noise rejection a little bit and see how this works. Oops, sorry. So here we have an access point with a bunch of customers, and if we go ahead and we hook up a traditional sector, you can see where the noise or low performance areas are of a traditional sector. And when you have customer connections within there and also noise reception at those rates, your overall throughput for that AP is dramatically reduced. Where with a symmetrical horn antenna, again, the coverage area is very precise, and the quality of connections within that coverage area gives you very high throughput, very stable link connections, and therefore very efficient use of the access point radio. If we look at the co-location capabilities of sectors versus horns, you can see here that, again, the co-location of multiple, oops, sorry, I apologize here. The co-location of sectors versus horns, again, makes it very difficult to cover the same area and add capacity by adding more sectors and covering the same area. So again, your overall throughput could be diminished somewhat, and the sharp angles and the narrow angles of horn antennas allow you to build a coverage area that allows you to segment the network and therefore add much more AP customer connectivity than with a traditional sector. So if we look at the traditional sectors, we say this is the old way versus the awesome way. Again, to kind of sum it up, a traditional sector again has bad edge of sector performance. It has high noise receiving capabilities through side lobes, and makes it very difficult to add AP density or AP connectivity by adding more traditional sectors and overlapping the same beams. With symmetrical horn antennas, you can take a 90-degree sector and segment that into 3 30-degree sectors, or potentially a 120-degree sector, and segment that into 3 40-degree horns to again get the same coverage area with non-overlapping signals, and therefore increase your AP density and increase the overall throughput to your customers. So that helps address the first issue of the growing demand for higher connection speeds to your customers. And then by adding the extra APs, right, and increasing your AP density, you're dealing with the second issue that's there, and that's the growing demand for the number of connections that you have to serve in today's networks. So one of the most common feedback or first thoughts about using horns and adding additional APs usually comes with channel availability. That's usually the first question. Well, customers will say, well, I'm looking, at the spectrum, and there just aren't any available channels for me to use. So how can I add a second or a third AP in the same coverage area if there's no channels available? And the problem that you're seeing, or the reason that you're thinking of that, is because you're looking at the spectrum through your traditional sector, right? So if you look at this setup here, you have one access point, AP1, that's transmitting on 5700, and then you have 2 other towers that are transmitting on 5500 and 5900. When you look at that spectrum, it looks like you have no channels available, right? But if you were to use a symmetrical horn, because there's no side lobes, the beams are very narrow, you'll actually see now that channel 5500 and channel 5900, again as an example, is now usable and available. And that's because, again, the horn antennas have very precise radiation angles, and they don't see very well beyond that. And with the absence of side lobes, you actually have a lot more spectrum that's usable. You just aren't seeing that availability because you're looking at it through your traditional sector at the time. So the use of horn antennas will help create more available channels. You just have to install one in order to see what the spectrum looks like through a horn rather than a traditional sector. So noise floor is yet another issue. One of the other most common feedback that we get, or skepticism about horns, is the lower gain, right? So horn antennas typically have a lower spec gain, especially in the wider sectors. People ask, well, with this lower gain, if I can't make the connections with a 19 or 20 dB sector, how can I possibly do it with a 16 or a 15 dB sector? And the answer there again is noise isolation, right? So if we look at the noise floor, again, when you're looking at it with a traditional sector, the noise floor and usable spectrum becomes much more unusable, right? So as other sectors go up on other towers, whether it's your towers or competitors, again, the noise floor starts to grow. And one of those reasons that the noise floor grows is, again, that a lot of the signal is transmitted in unintended directions. So again, by using a symmetrical horn, it helps filter out a lot of that noise. So even though you may have lower forward gain, you have much better noise, signal to noise ratios, right? So by eliminating noise, you can actually still go and provide service at the same distances, in some cases, not all, but in some cases, because the SNR increase that you see by reducing noise overcomes that reduced forward gain number that some of the horns have. Also, because horn antennas, again, in the wider beam patterns, have lower forward gain, which is a fixed input gain to your radio, you hear noise at a much lower intensity than you do with higher gain antennas, because again, the antenna gain is fixed. So your input receive sensitivity, or your input receive intensity, is fixed by the gain of that antenna. So by having a lower gain or a lower forward gain horn, you're hearing noise at a lower level, and therefore it could make channels usable that weren't usable before. So now we'll talk about massive scalability. So massive scalability is really where we're trying to get today. Again, the demand for the number of connections and the amount of throughput per connection is growing at a very fast rate. So in order to be successful today, you need massive scalability. And the only way to really achieve that is with symmetrical horn antennas, because we have such narrow beam horns. You can again increase the AP density in your areas where it wasn't really available before with traditional sectors. Again, with the co-location on your towers and the interference from other towers, we're easily able to eliminate that and increase throughput by using much cleaner signals, adding more AP capacity, and therefore getting much higher densities by reducing the noise, not only hearing noise less, but also sending noise, not as far away as traditional sectors. And really, this is the only way to achieve massive scalability. So again, the technology that's needed for fast, sustainable wireless is horn antennas. Again, with our twist port technology, gives you the massive scalability that's needed in order to fill the need for the growing demand of internet today. Increasing throughput with horns, also saves you money, because you can use, radios that don't have GPS. You also don't need to always run wider channels. In some cases, you can deliver more throughput or equal throughput in a smaller channel. So a 40 megahertz channel can, in some cases, deliver the same type of throughput to your customers than a, let's say, sloppier antenna on an 80 megahertz channel. So again, this all comes down to your ROI, saving money as well, by maybe even taking the older technology that you have on your towers, just by adding horns and making it deliver more throughput. So it can help save you from having to forklift your whole network, or maybe reduce or widen the amount of time to give you more time to grow out your network, and again get your return on investment on the previous technology that you had out there. So it definitely gives you a lot of options when you use horn antennas compared to traditional sectors. So we urge you to join the community, become a user. We have a pretty active forum, and it can be found at rfelab.com. Lots of good customer feedback there, a lot of good seasoned users. If you have questions on how to use horns, the community can help you get through those questions. We have a lot of great customer feedback and a lot of information on our YouTube channel. So I would suggest that if you haven't, go to youtube.com/rfelements and check out our videos that we have there. These are customers telling you how these antennas work and help their networks grow, not just us, the vendor, telling you that the antennas will do it. So you'll hear from WISPs just like yourself. Many of them might be in the exact situation that you're in, and you can again see how this technology has helped change their business, grow their user base, and again be able to deliver much higher quality connections. We're very active all over on social media. Again, we just talked about our YouTube channel. We're very active on Facebook, LinkedIn, Twitter, pretty much every social media platform that there is. So we urge you to, again, if you're on these social media platforms, to look us up and get involved. Where we make ourselves available to help you with designs of your networks as well. If you have questions on installation or how to deploy any of our antennas in your WISP, you can always email us, info@rfelements.com, or ping us on one of these social media platforms. That's all I have today for this Increasing Throughput 101 webinar. So if we have any questions, I'd be happy to take them.
Thank you very much, Tassos, for that presentation. We enjoyed it very much. And yes, I do have some questions for you. I'll go ahead and get started with the first one here. You had mentioned that RF Elements is based in Slovakia, but for those of us who may not know, can you tell us where your products are manufactured?
Absolutely. So like most products, they're manufactured in China.
Okay, awesome. Thank you. Next question. What type, you did go over that, where you're in social media and all kinds of stuff like that, and your support. So can you expand on what type of support is offered throughout the channel?
Yeah, so throughout the channel, we have many distributors in the U.S. that can help, as well as ourselves. I'm based out of Texas, so I'm here in the U.S. I serve the Americas mostly, Mexico, the U.S., and Canada. It's all done generally through email support, right? So you can, again, email us at info@rfelements.com. We also have an RF Elements English Facebook page, as well as our web page as well. So you can private message us through, again, any of these social media platforms, and and get us direct. Response time has been pretty fast. I mean, usually it's an hour or less. Sometimes it's instant. So again, if you have any questions, try it out, right? Go on Facebook, ping us, and you'll see we're pretty responsive as soon as the questions come in, and either dealing with an email or talking to you direct. And we can also, once you engage us with a problem or a question, whatever it is, if it requires a phone call, we'll set up a time to get on the phone and talk you through whatever your problem, or answer whatever questions that you have. So we're pretty much at your disposal.
Excellent. Thank you very much. I'm going to go on to our next question. It says here, with your TP adapters, I know you make devices that work with other vendors as well. Which vendors do you have TP adapters for that may already be in use today without these adapters?
Yeah, so we support 4 main radio vendors with twist port adapters. That's Ubiquiti, Microtech, Cambium, and Mimosa. For Cambium, we have a twist port adapter for the EPMP 1000, and we just released now a twist port adapter for the EPMP 2000 radio platform. For Microtech, we have one twist port adapter that allows you to use any router board 9 series. So if it's a 911, 922, 921, basically any router board that's that small square form factor, even 411s with mini PCI radios. So practically any small form factor Microtech router board. For Ubiquiti, we have a whole slew of twist port adapters, again, for all their radio platforms, whether it's the Prism or the Gen 2 Prism. We have a twist port adapter for that. The old Rocket M5, the older Rocket AC lights, the Rocket PTP. So pretty much every adapter. We also just released, and it'll probably be out in December sometime, a new adapter for the Ubiquiti ISO station and Prism station. So if you've seen the kind of pigtail-less waveguide fed radio interface radio system that they have now, we have an adapter that you can put in that, so that way you can use those radios with our horn antennas. So really, it's not just about the horns, but any RF Elements twist port enabled antenna, you can use any of those radios with them. And for Mimosa, we also have a newly released C5C twist port adapter. So the C5C is that small, little client radio, and I believe you'll be able to use it for point-to-point as well. So we have a twist port adapter for that. Now, for any other radio system that we do not have a twist port adapter for, we have our carrier class horn. So the carrier class horn is pretty much identical to the twist port horn as far as performance goes. It's also available in all the same beam patterns, everything from a 30-degree wide up to a 90-degree wide in 10-degree steps. So we have a 30, 40, 50, 60, 70, 80, and 90-degree horn. The difference is it does not have a twist port interface. It has two end connectors on there. So if you have some other random or very large form factor radio, like let's say the Mimosa A5C, it's a fairly large radio, and a twist port adapter isn't really suitable for a radio that large. We have, again, connectorized carrier class horns that will allow you to interface that radio through LMR cable and still get the same horn performance.
Tassos, thank you very much for that. I'm going to go on to our next question here. Mm-hmm. How does the noise rejection compare in regards to the IS5AC? Are there any cross comparison sheets that we could read?
I'm not sure what the IS5AC is. Oh, the ISOstation 5AC. I
believe
don't.
It's the Ubiquity version, they said.
Okay, so the Ubiquity horn, it's actually quite different. Again, it depends on which width we're looking at. Our antennas typically have slightly higher gain. There's multiple Ubiquity antennas out there as well, right? So they have some asymmetrical horns as well. And if I don't have slides or animations to show you, but actually the RF performance of the asymmetrical horns compared to our symmetrical horns is night and day difference. It's nowhere near as clean. They still have large complex side lobes, and the horizontal and vertical beams are not identical, right? So you have very wide variations between the vertical and horizontal beam pattern. So you get that same uneven coverage area throughout the coverage area. Now, it's still a horn, so there is some benefit there, but not, just because it's a horn doesn't mean you're going to get superior performance. It has to be the correct type of horn. It has to be manufactured correctly and made with high quality parts as well. So not all horns are the same. If you have a horn antenna, it doesn't mean you're going to get superior RF performance. So we believe that there's definitely a difference. But again, we were talking about symmetrical versus asymmetrical as well. So there's some other differences in that type of technology or that type of horn technology.
Thank you very much. I've got a comment here where when you show the old versus awesome, we're going to go with awesome every time. So
Thanks.
There's that. Got a last question here for you. Sure. Does the horn antennas also support 2.4 gigahertz and 3 gigahertz?
No, unfortunately not at this time. They're only available for the 5 gig spectrum. 2.4 is more than likely a no-go for us, and mainly it's because it's just too big, right? So as you go lower and lower in frequency, the horn becomes much larger, right? So a 2.4 horn would be, about double the size of a 5 gig horn. It's not to say that we're not set right now as 100% no for 2.4. There's a slight possibility, but it's not on our 12-month roadmap. Let's just say that. Now, 365 is something that we're looking into, and you'll probably see. Again, I can't give you an exact time frame, but it's definitely something that we'll probably see sometime here in the near future for LTE.
Oh, Tassos, thank you very much for answering those questions, and thanks to everyone for attending today's webinar. If you have any other questions, please feel free to contact your sales rep or email us at sales@microcomtech.com. If you wish to view any of the products mentioned or shown today, please visit us at www.microcom.us. And remember, this webinar presentation has been recorded and it will be uploaded to our Microcom YouTube channel. So if you would like to view it again, you certainly can do so on YouTube. Thank you, Tassos, again for your time and all of your information this morning. Thanks everyone for joining. Have a great day.
Thank you. Bye.